Assalamualaikum and hello everyone. My name is NADHIRAH. My matrix number is 225186 with my team members SIOW 225639, Muhammad IZZUL IQMAL. Number matrix is 223602 and AHMAD HUZAIFAH. Number matrix is 222408. Today, we will present about the mini project in production of weak nitric acid, which is 70%.
Hello, my name is SIOW, matrix number 225639. So let's start with a little intro about nitric acid. Nitric acid, HNO3, is a colorless, filming, and highly corrosive liquid that is a common laboratory reagent and is an important industrial chemical for the manufacture of fertilizer and explosive. It is toxic and usually can cause severe burns. Its freezing point is at negative 42 degrees Celsius and its boiling point is at 83 degrees at 1 atm.
Hello, my name is HUZAIFAH bin HATTA. My matrix number is 222408. So I will explain about nitric acid production condition that has been given to our group. So we required to produce the weak nitric acid with 70% volume per volume. We also been given feed material, which is liquid ammonia, also with the feedstock of 500 kilotons per annum. And we use the method mono medium pressure to produce our nitric acid. So next I will explain about post-watt process. This process is used to produce the nitric acid. So there are three steps involved. First of all, oxidation of ammonia. So ammonia is oxidized by air in the presence of catalyst, which is platinum rhodium, and the reaction between ammonia and oxygen produce heat, which help to maintain temperature of the reaction. Next, we have dissociation of nitric oxide. So the nitrogen oxide will react with water and oxygen to form nitrogen dioxide. This reaction occurs in different chamber from the first step. And the last step is oxidation of nitrogen dioxide. The nitrogen dioxide will be absorbed into water to form nitric acid. The absorption typically occurs in absorption tower, where the gas bubbles will go through the water. That's all from me. Thank you.
So now let's move on to a material safety data sheet, and it is a document that contains information on the potential hazard and also how to work safely with these chemical products. So let's start with our main feedstock, ammonia. Ammonia is very toxic and also can cause severe skin burn and eyes damage. So when you accidentally skin contact with it, you should wash the affected area with soap and water and rinse the exposed skin gently using water for 15 to 20 minutes. And when you accidentally eyes contact with it, you should also rinse the exposed eyes gently using water. And when you accidentally swallowing it, you should rinse your mouth thoroughly and do not induce vomiting. So next is our main desired products, nitric acid, HNO3. Nitric acid is very toxic as well to human. It will also cause severe skin burn and eyes damage. It may also intensify fire. Therefore, when you accidentally inhale it, you should remove the victim to the fresh air and keep the rest in a position that's comfortable for breathing. You should also take off immediately all contaminated clothing and rinse the skin with water. And it should be kept away from clothing and also other combustible material.
This is the overall block flow diagram based on our research. Okay, the ammonia and air we use as feed in these productions. First of all, we need to produce nitric oxide from catalytic oxidation process in reactor 1 of ammonia and oxygen. Of course, it will be produced in gas mixture. So we put gas liquid separator or condenser to remove unwanted component like ammonia and water by dew point temperature. Then, in stream 2, nitric oxide need to be oxidized into nitrogen dioxide in second reactor, or we known as oxidation reactor. Next, this is an important unit for the production of weak nitric acid, which is absorption tower, where nitrogen dioxide will react with water to produce nitric acid. Based on our research, absorption tower only can produce 40% to 50% of nitric acid. So, we decide to put evaporator unit to achieve 70% of production with nitric acid by boiling point temperature. Okay, this is just a simple explanation of block flow diagram. In detail, each unit of reactors may have side reactions they need to be considered. Now, let's hear the details from my team members.
Thank you, Eva, for explaining the overall block flow diagram. I will continue with the first reactor in nitric acid production, where our first reactor is catalytic oxidation of ammonia unit. In this reactor, our feedstock, liquid ammonia, is first vaporized into ammonia gas. After that, the ammonia and air are introduced into the reactor 1. Then, the ammonia gas will undergo oxidation to form nitric oxide gas, NO, which is our first desired product for our first reactor. And the condition needed for this reaction is 998 degrees Celsius and medium pressure of 4 bar. This is because at high temperature and low pressure, the oxidation rate of ammonia will increase and will greater the yield. The catalyst used here is 90% of platinum and 10% of rhodium. Then the two reactions that involve here are these two. For the first reaction, nitric oxide gas is formed as our desired products. For the second reaction, nitrogen gas is produced as unwanted product. Both of these reactions yield byproduct H2O. Therefore, our outlet of this reactor consists of unreacted NH3, O2, N2, and water as byproduct, and lastly, NO gas. Let's move on to the calculation. I will take 100 mole per hour of ammonia as our basis in this case. But before that, let's take a look at other information here. From these three literature I found online, I found out that we should introduce a ratio of 1 to 9 volume percent of ammonia in A into the first reactor, which means when I introduce 100 mole of ammonia gas, 900 mole of air should be added also. Next, the selectivity of NO to N2 is 9.9. Lastly, the fractional conversion of NH3 is 0.96. These three other info allowed us to make our DOF to become 0, and we can start our calculation now. For the calculation, I'm using the extent of reaction method in order to calculate the outlet molar flow rate by using 100 mole per hour inlet ammonia and 900 mole per hour of air. And let the extent of reaction become X and Y for easy understanding. Then I set up the equation for all components here. After that, I substitute the equation and rearrange them to form two new equations here. Then solve it simultaneously and we will get our X and Y value. Substituting back into the reaction equation here, and we finally get our outlet molar flow rate for all components. And for your information, we can change the basis here wherever you want. Then all the result here will automatically change as well. Not to forget, this is the information of all components in the stream 1 inlet stream and the stream 2 outlet stream here. After calculating the mass flow rate from the molar flow rate, the mass flow rate is balanced. So that's all for my part. Thank you.
Next, for second unit, which is condenser or gas liquid separator. We know from unit 1, we have a gas mixture that contains nitric oxide, air, ammonia, and H2O. So the intent of this unit is to remove unwanted component, which is ammonia and water, by dew point temperature. We need to use Rod's law to determine the temperature based on the fixed mono medium pressure, which is 6 bar. In this unit, we only need nitric oxide with air to the next oxidation process, which is reactor 2. The step to solve all the unknown is, first thing first, we need to use the N coefficient from table B4 to find the pressure dew point or saturated pressure. Then, if there is any difference, we need to change the temperature until this error obtained is 0. After that, we have to use this Rod's law formula to get mole fraction of condensate, which is ammonia and H2O. Lastly, we can find all the unknowns, but make sure mass in is equal to mass out.
Next, I will continue with oxidation reactor, where this unit is used to oxidize nitric oxide to form nitrogen dioxide, where nitric oxide will mix with oxygen to increase the oxidation number to form NO2. So the temperature and pressure condition for my unit is temperature with 473 Kelvin, which is 200 degrees Celsius, and pressure 4 bar. So we have other info to other info, which is equilibrium constant 6.5 and fractional conversion of NO 0.98, and we have basis with 100 mole per hour for each stream in, and reaction involved is 2NO plus O2 to produce 2NO2, and 2NO2 will convert into N2O4. For stream info, we have 3 streams. So first stream we have nitrogen oxide, nitrogen and oxygen with molar flow rate 100 mole per hour and mass flow rate 3036 gram per hour. For stream 2, we have nitrogen and oxygen with molar flow rate 100 mole per hour and mass flow rate 2084 gram per hour. In stream 3, we have nitrogen oxide, nitrogen, oxygen, nitrogen dioxide, and nitrogen dioxide with molar flow rate 124 mole per hour and mass flow rate 5931 gram per hour. So for mass balance, which is mass in equal to mass out, we have equal value, which is 5921. For calculation part, I use extent of reaction equation to solve this problem. So we have 6 equations in total to solve the problem. So the outcome is we have 5.6 mole of NO2, 1.6 mole of NO, 36.4 mole of N2O4, 0.8 mole of O2, and 80 mole of N2.
So, hello and hi everyone, my name is Muhammad IQMAL bin BAHARUDIN. My metric number is 223602. Okay, moving on to the next chapter, I will explain a little bit about absorption tower. The primary function of absorption tower is to transfer a specific component from a gas stream to a liquid stream. In the case of nitric acid production, it's responsible for absorbing nitrogen dioxide, which is NO2 gas, from the hot gas mixture, leaving the oxidation reactor and dissolving it in a strong nitric acid solution to produce weak nitric acid. Next, from the block diagram itself, there are two streams going in and two streams going out. Let's focus on the stream 1, which is contain nitrogen dioxide, nitrogen oxide, and nitrogen tetroxide, oxygen, and nitrogen. Then, the components outlet of this reactor is nitric acid, nitrous acid, and water, while the other components will leave this reactor as a tail gas. Next, as you can see in this slide, there are three chemical reactions involved in this reactor, where the main reaction is nitrogen dioxide react with water to form nitric acid and nitric oxide. Lastly, I will talk about the condition of this reactor, where the temperature is 40 degrees Celsius and the pressure is 4 bar. From the research I do before, the other information I got is the fractional conversion of NO2, which is 80%, fractional conversion of N2O4, which is 70%, and the yield is 98%. By considering all of this additional information, we can perform calculations to determine the outlet condition for this absorption tower. For this part in our project, we use a extent of reaction method to calculate the outlet for this reactor. The other information is used to help you solve all the equations. And once the value of extent of reaction for each chemical reaction is found, you can calculate all the outlet based on the extent of reaction equation before. As you can see in the middle of the slide, there is a result for outlet for this absorption tower.
This is the last unit, which is evaporator. We know that nitric acid and several components have been produced from previous unit, but it's only produced 40% to 50% of nitric acid. Our group are required to get 70% of weak nitric acid, so we have to add this evaporation process to achieve 70% of nitric acid. The intent of this unit is to evaporate the liquid mixture by boiling point temperature. This unit also uses Rod's law to determine the boiling point temperature based on the fixed monomedium pressure. The step is same with the condenser. We need to find the M10 coefficient, but nitric acid is not listed in the table before. Did some research to get more information about M10 coefficient of each NO3 from the article that relate to this situation or the production of weak nitric acid, and do some mass balance. So lastly, we can find all the unknowns, but make sure the mass in is equal to mass out. That's all from us. Thank you.